All right, Matthew. You're good to go.
Alright, I guess I'm gonna start the timer on my end so I have a good representation of how long it takes. Hello, my name is Matthew Anderson, and my senior capstone project for 2025 is designing a flow meter for measuring flow in natural bodies of water. So to start with my project motivation, what inspired my project? So I recently had a coastal engineering internship where I conducted something called a hydro flushing analysis. This is where we relied on something called the orange test to measure water velocities in marinas. Now, an orange test is simply what it sounds like, where we, as you can see in this photo right here, we threw an orange in the water and we measured distance over time to get water velocity. Now, this was wildly inaccurate, and this was mainly due to a broken flow meter. So that got me researching. Some of the commercial options that were available were very overcomplicated, fragile, as the one in our firm had broken, and they weren't really suited for low flow conditions in marinas. This experience highlighted the need for a simple, reliable tool for measuring water velocity in coastal environments. So I'm going to start with why this matters, and also give you more background on what a hydro flushing analysis is. So basically, a hydro flushing analysis evaluates how effectively tidal flow disperses pollutants like oil, sediment, and waste from marina basins. This is because poor water circulation can lead to stagnation, hypoxia, and degraded marine health. This is mainly for ecological reasons. So we measure water velocity. This is mainly critical for environmental permitting, for state permits, and sustainable marine design and monitoring to improve water quality. So this is an example of a marina that was conducted in Florida. This is not one that I did, and this is a chart of a hydro flushing analysis. So the pollutants, like I mentioned before, the oil and sediment, need to be dispersed within a specific marina study within 2 tidal cycles, or 4 tidal cycles. And this is an example of that. This was an actual hydro flushing analysis conducted by another coastal engineering firm, where the red is the concentration of pollutants. As you can see, it's assumed to be 100% volume, and over the course of roughly a day, after 24 hours, you can see that it's mainly gone and dispersed, and definitely after 72 hours. So this is an example of a successful hydro flushing analysis. Some of my objectives for this project from the beginning was I want to develop a flow meter that's optimized for low-speed tidal flows in semi-enclosed marina basins. Now, I wanted to achieve a water velocity accuracy with an error margin of plus or minus 5%. I picked this accuracy mainly due to physics lab error margins. I wanted to design it for field usability, focusing on compactness, ease of transport, and maintenance. I wanted to lower the overall system cost compared to commercial alternatives without compromising reliability and accuracy. I also wanted to enable real-time readings through an onboard OLED display, and also ensure durability in open water conditions with a protective sensor housing and corrosion-resistant components. Now, my design is can be broken up into 2 main components, mechanical and electrical. So we're going to start with the mechanical design. All of these components were designed in Fusion 360 and 3D printed using a F1 carbon printer. And so here's the overall three things that I designed and printed. So we're going to start with the propeller sleeve. This basically encases the internal propeller assembly, which includes a propeller shaft and bearings and a couple other components that we'll get to in the next slide. This ensures proper alignment with smooth rotation and flow within the stream. So this is what holds the propeller. The second is the enclosure seat. This is what is right here. So this basically holds the watertight electronics enclosure, which holds the PCB and all the electronics that's needed to read all the readings. The third is the propeller shield. Now this is broken up into 2 parts, the top and the bottom. Now it's broken into 2 parts because I want it to be easily taken apart in maintenance in case you wanted to fix the bearings or lubricate anything, or in case anything got damaged. Moving on to the propeller assembly, like I mentioned in the last slide. So as you can see, this houses and aligns all the rotating components. So here's an overview of the components. You have a cap nut, which secures to the end of the shaft, the propeller, the drive dog, which links the propeller and the drive dog to the shaft to keep it as almost like a set screw to ensure that it rotates about the shaft. The shaft, which everything's aligned on. You have the washers, the ceramic bearings, which are right here. And the ceramic bearings are going to sit in this little groove right here on each side to kind of hold them in place. The propeller sleeve, which is this, like I mentioned in the last slide, and also the set screw collar, which secures everything and makes sure nothing shifts and falls off of the shaft. Moving on to my electrical design. So I knew from the beginning, after a couple weeks of research, that I wanted to use a magnetic sensing system. Now, there's two options that I had. A linear Hall effect sensor or a reed switch. Now, so a Hall effect sensor basically has no moving parts, unlike the reed switch. And it does offer, can I restart on the side? Do you mind cutting it out? I started, I skipped the magnetic.
Do it again, yes.
Alright. Okay. Let's do this. So, moving on to the electrical design, I knew from the beginning that I wanted to use a magnetic sensing system. Now, magnetic sensing tracks water velocity by propeller rotation, which is the bread and butter of the project. So this works by magnets being attached to the back of the propeller, and every time the magnet passes whatever magnetic sensor that I decided to use, it picks up a magnetic current and it counts as a pulse. Now, there's two types of ways it can, there's two types of magnetic sensors. You have Hall effect sensors and reed switches. Hall effect sensors, like the one seen here and also here, basically measures voltage. Now this specific one has no moving parts, and it can output variable voltage based on magnetic field strength. So as you can see, this magnet going up and down, it measures a constant 2.5 volts. And when the magnet passes, it jumps up to 5, and that's what would be considered a pulse count. Reed switch, as seen here and here, is more like on and off switching. There's something inside of the reed switch that physically opens and closes due to a magnetic current being picked up. Now, the downfall of the reed switch is that it doesn't have unlimited switching cycles, which is, if you're measuring a lot of water velocity, it could go out or be broken and damaged and need to be replaced in the future, while the linear Hall effect sensor, after a couple of years, has unlimited switching cycles, so it would never, in theory, need to be replaced. So this is what I selected, the linear Hall effect sensor. Moving on to the main idea of my electrical design. So it has a couple components. Obviously, what I mentioned before, the Hall effect sensor here. The custom PCB, which is just a board that basically connects all the electrical components. It's just a green board that all these components are soldered to. You have the OLED display, which is right here. I have my ESP32 development board, which processes the data and calculates all the velocities of what you put the code into. You have the LED and resistor, which can be seen right here and here. So this basically acts as a visual display for the user to see if a magnetic current was picked up or passed. And I also have the bag, which makes it deployable in the field without need of cable. Moving on to the overall system assembly, I have all these pictures. So this is a 3D model of it. The handle is roughly 3.8 feet in length, and side next to it is the real life thing. This is also a closer look of the 3D model of the PCB inside the waterproof enclosure, as well as the bottom components with the top and bottom shield, the propeller, and all of its components. And here's a real life display of this. So moving on to the budget, This was a project that was supported by the Decker Eagle Spur grant, which I was given $400, and this was the main source of funding that helped me develop this project. So some of the main components, I already mentioned a couple of these, but some of the main components that I used to help build this project was PETG filament. This was what was used to the 3D printing filament for all my mechanical parts, my custom PCB, the bearings, my propeller, waterproof enclosure, the aluminum handle, the propeller shaft, the battery, fasteners and mounting hardware, and also some seals and adhesives which I use to connect some things like the Hall effect sensor to pot it to make it more waterproof, and some miscellaneous parts. So this included like things for testing like a breadboard and wiring. And I managed only to spend about $309 all said and done. So moving on to testing and calibration. So I can't just put it all together and throw it in the water and pray that it reads the correct velocity. I need some way to experimentally test it in a controlled setting so I know that whatever was being displayed on the OLED was correct. So the way I did this was I used a stepper motor, and this is basically something that spins, and I put a little propeller on it that I can put a set RPM into that I would know would be accurate, and I would compare it against the firmware that I had written for my Hall effect sensor. So yeah, so basically what you can see here is the Hall effect sensor, or this is the stepper motor with the propeller and the magnets. And I have a magnet on each blade as you see here, and when, like I said before, when the magnets rotate and pass under the Hall effect sensor, it's going to count as a pulse. So this is what's being shown here. So this is very timely, my Hall effect sensor that I have set up, and these are the magnets. So I would put a set RPM in here, let's say 80, and when it would spin, this would count the magnets as they pass by, and then produce a corresponding velocity measurement. The main measurement that I used was meters per second. It could have been anything like feet or knots, but I picked meters per second. After hundreds of tests, anywhere from 0 to about 200, I have an average error about roughly 1.5%, which does confirm my system's accuracy in low speed flow conditions. There's a lot of things that I could have done differently. So obviously I wish I started calibration earlier, so I know everything was more correct. I wish I ran more tests. I wish I designed an adjustable handle. It's something that could have easily been integrated. I just didn't feel that was necessary at the time. I wish I tested my system in more variable flow conditions for more RPM testing, which is when you have a flow, let's say 10 meters per second, and it goes up to like 12 and then back down. I just tested it at set RPMs. I wish I started coding and designing the components much earlier instead of doing research all first semester, so I could have designed something probably more complicated and better. Some of the future directions and next steps that I would personally take in this project if I had more time would be the implementation of wireless data transfer. Basically, this would be an interface that logs each data point, which is velocity in our case, with a timestamp, and it would generate real-time graphs so you could visually see the water velocity in a more user-friendly manner. This wouldn't have been hard because the microcontroller that I used for this project does have built-in Bluetooth and Wi-Fi capabilities, which could have been leveraged to enable this feature. I wish I explored using multiple Hall effect sensors. In some of the research articles that I read throughout the course of this project, I saw that a lot of people, for a lot bigger projects than mine and more complicated, use multiple Hall effect sensors to increase accuracy. This also in turn reduced false readings and did enable better tracking of partial rotations or inconsistent flow, which mine does not take into consideration. One of the biggest things that could be done is developing a fully controlled testing environment instead of just using lab testing using the stepper motor. And this would be, in my eyes, something similar to a trough, like shown here, which you could have a known flow velocity through. This would simulate real-world conditions while maintaining consistent and repeatable calibration variables. So this is just more of a way for my propeller to be actually tested in water and see how that acts. Some of the key takeaways I have for this project, so I gained a lot of skills, either both technical and soft skills. So some of my technical skills that I gained through this project was obviously programming in C++. I learned a lot more about modeling in Fusion 360, circuit integration, electronics design, whether that be my Hall effect sensor, the testing and setting up of the stepper motor, or even hooking up the OLED. Sensor calibration. Before I started the project, I didn't really take into consideration that the experimental and testing needed to be really close to what would actually be used in the field, and that was a kind of a learning curve. 3D printing, I got pretty good at 3D printing over the course of the semester, and also mechanical assembly. Some of the soft skills that I had gained throughout this semester was problem solving, where when parts broke, or the sensor misaligned, or the data didn't match. Time management is probably the biggest thing that I've learned. You have a lot less time than you think throughout the semester. And balancing research and testing along with other classes can be quite a juggle sometimes. Also, technical communication. The weekly reports and the presentations have majorly helped me in speaking in front of crowds, and reporting on technical things like, I don't know what to say there. Whatever. I guess I'll redo the technical communication part. So I also learned technical communication, which translating things that you've done throughout every week and your design process into engineering terms, or turning it into visuals so other people who have no idea about your project can understand can be difficult. And it was kind of fun learning how to project how and why I made design choices. So moving on to my conclusion, this project did give me hands-on experience developing a custom flow meter designed for low flow tidal speeds and marina basins. I learned how to turn field-based challenges into a working engineering solution through iterative design, calibration, and testing. My final design is accurate, durable, and cost-efficient compared to the commercial off-the-shelf options that I mentioned before, which does make it a promising tool that could be used for hydroflushing analysis and environmental monitoring. One of the unexpected realizations that I had throughout the semester was even small details like how a magnet is mounted, or where the Hall effect sensor is, or how it's potted or placed, can throw off the entire system, especially when a detection range is, millimeters apart. So I did learn that precision does matter at every level, even in early prototypes, and you should take every factor into consideration. Questions?
So, if you had more time to work on this project, would you consider having anything that any of your custom parts machined instead of 3D printed?
Yes, I would actually explore all of my custom parts being machined just for, like I said in the shield, the original plan throughout the semester was to get it machined in clear polycarbonate so you could see kind of all the components that sat in there. But due to time constraints and budget constraints mainly, I had to just opt for 3D printing.
The magnets on your propeller, you have one magnet on each blade of the prop. Are they all the same polarity, or do you have one
Yes,
that's
so
north out and the other two are south out?
So when I mentioned how linear Hall effect sensors work, the polarity does matter. So in this example, the voltage is going up. It's using the south side of the magnet, and if, let's say for this specific one, if you use the north side, the voltage would go down. So all the polarity is for mine, at least for the south pole of the magnet.
So all three magnets are south facing out?
Yes.
Okay.
Because if in the code I have a threshold voltage, which is above whatever the sitting voltage, in this case it's right here, 2.5. So when the south side passes the Hall effect sensor, this magnet passes the Hall effect sensor, it will go up in voltage, and that will count as a volt count. Now if I had the north side, it would go down and wouldn't count it at all.
Could you have had one where the polarity, let's say you're counting the south poles, if you had one with the south facing out and the other two with the north facing out, would that aid when you have high RPMs and the Hall effect sensor is having to
Yes.
determine what blade?
That's one of the things that I was looking into at the very end of the project, taking off two of the magnets and putting counterweights, because sometimes they're just too close together, and in the high RPMs it kind of gets, it will hold a voltage and it'll just, the RPMs will go crazy. So if I, let's say, kept this one and took these two off, it might have more time to compute and recognize the voltage change.
In the beginning, you said that your Hall sensor reads 2.5 volts. That's without magnetic field. So does it then go to zero if you swap the magnet around?
Would it what?
Does the voltage go below 2.5 if you hold the magnet the other way? Can it sense?
Would. It depends on, from my experience on how I understood and coded my Hall effect sensor, if you had the voltage threshold set below 2.5 and it went down, then it would count.
Oh, your voltage threshold is 2.5. It's not.
Yeah.
It reads 2.5 if there's no
Well, the
magnetic
threshold
field.
would be between, would be above 2.5. So if it reads 2.5 with no magnetic field detected, then the threshold would have to be above that. So when the magnet passes it, it increases in voltage.
Well, my question is, if you have no magnet at your Hall effect sensor, is the output 2.5 volts?
Yes.
And if you have it the right way, it jumps up to 5. If you have it the other way, does it then jump below 2.5 and then reach 0? Is this?
Yeah.
Okay. Also, at one point, you were considering actually testing your system in water. With the boat, has this not happened, or?
This hasn't happened yet, just due to time constraints, but I probably will. I'm going to make the necessary adjustments and see how removing magnets affects the higher RPM readings, because I kind of wanted to count a wide range of RPMs, not just low flows, and kind of optimize that. But after I explored doing that, I did want to test it in the water. But this could hypothetically put in the water right now and count. I just wouldn't know if the calibrated known water speed, it would just read something and I couldn't trust that that was the correct RPM reading.
The actual
Yeah.
hardware.
I think I could go to, let's see,
Yeah, perfect.
this one.
And I'll show you.
Is the camera over there?
It's
Oh,
used
right
there.
here. So
Perfect.
this is the entire thing. So this is 3.8 feet. It's not the length is not specific to anything. It's just I'm short and I didn't want it taller. But yeah, you can see I have a hole cut here for the wiring for the Hall effect sensor to go down. Bring it closer. Is
Yeah,
that
it's probably better if you stay. I don't know if this autofocus is.
But yeah, so the Hall effect sensor sits on top of here, and if you kind of look, I don't know if you want to zoom in, but you see the magnets on the back of the blade. When this spins, that's when it picks up the magnetic pulse, and then it transmits the data all the way up to here, which is the microcontroller.
Right. You need to figure out how to secure your battery.
Yeah, I left a space because I wasn't sure at the time
Right.
what size was going in there, but yeah.
Very cool. If you talk to your former employer and told him what you got?
I haven't. A buddy of mine was old, about to retire, but he told me to. They were the inspiration for this project, so he told me to, when I finish up my poster design, email that to them and just tell them that thank you for giving the idea and show them that I developed something that we had issues with back in the day. So
Yeah. And it looks like it's close to your parents' place, right? Where they,
yeah, South
So
Florida.
maybe over the summer, if you go on vacation, you can bring it and maybe
I could, yeah.
compare it to one of the orange tests.
Oh, yeah. That would be fun.
Calibrated using the orange test.
Yeah.
Calibrated using the orange
That's
test.
right.
That was, I considered it forbidden, but we went with something more technical.
Cool. Well, let's give him another hand.